Hi guys, once again. So we have a problems here, problem based on physics mechanics, and then the elasticity. So now this is the question that we have here. We have the question says that a copper cylinder and a brass cylinder are stacked end to end as in the drawing, and say each cylinder has a radius of 0.25 centimeters. A compressive force F is equal to 6,500 newtons applied to the right end of the brass cylinder. Thus, find the amount by which the length of the stack decreases. And they given us the properties of the material. So now we can take down the data. So now we have a force, an applied force, compressive force, which is 6,500 newtons. So, and we also have what? We also have, they're saying each cylinder has a radius, they have equal radius of 0.25 centimeters. And then also now what we have, they are saying now a compressive force of 6,500 is applied to the right end of the brass. That means here we have a brass, and then here we have copper, and then now is on the right end, and they're saying find the amount by which the stack decreases. So you can see here we have 3 centimeters for copper, and then for brass we have what? We have 5 centimeters. So we want the amount by which they will decrease. So we know that now the change in length is equal to, is the same as what? Is equal to the change in length is the same as force multiplied by length initially over area multiplied by Young modulus, because we know actually that the strain is equal to the change in length over the initial length, and then that's going to be the decrease in length by how much it changed, and then divide by the initial length. And then we also know actually that the strain is equal to the stress divide by Young's modulus. So from these two equations, we can actually now equate them to say now the stress over E, Young's modulus, is equal to this change in L over L initial. So you can see now that the change in L should be equal to the stress multiplied by L initial over E. But we know that the stress is equal to force divided by area. That means change in L in place of stress will be force times L over area multiplied by Young's modulus. So that is how that equation can be shown or can be derived. So from there what we can do now, we do know the radius, we do know the force that was applied. So we can say now change in length of the brass will be equal to the force, and then they are experiencing the same force, which is 6,500 newtons multiplied by the initial length of the brass was 5 centimeters, that is 5 centimeters divided by A, and then the area there obviously is pi over 4 into D, and then the diameter, or let's use pi r squared. The area is equal to pi r squared. That means we're gonna have pi into our radius, and then that was 0.25 squared multiplied by Young's modulus. And Young's modulus, let's just change them to meters, because our Young's modulus are given that Young's modulus is equal to, and we need to be careful, we are dealing with brass. So the Young's modulus were given in the question for brass, that is 9 times 10 raised to 10 newtons per meter squared. So if we have that Young's modulus 9 times 10 raised to 10 newtons per meter squared, that means here we can have pi into that means the length of the brass is 5 centimeter, which is 5 times 10 to the minus 2. and then also we have here 0.25, which is 0.25 multiplied by 10 to the minus 2 squared, so that's pi r squared, and then multiply by multiply by the Young's modulus, which is 9 times 10 raised to 10. So let's see what we get here. We have 6,500 multiplied by 5 multiplied by 10 to the minus 2, and then divided by pi into 0.25 multiplied by 10 to the minus 2, and then squared multiplied by 9 multiplied by 10 raised to 10, which is the Young's modulus of the brass. And then what I get is 0.0001839 meters, which is also equal to, if we multiply that by 1000, multiply by 1000, that's going to be 0.1839 millimeters. So that's the change in length for brass. So because they are in parallel, they are experiencing the same force. Because they are in series, they are experiencing the same force. So now we need the change in length of the copper. So the change in length of copper also will be force multiplied by initial length over area multiplied by E. And then the force that was applied is the same for both, which is 6,500. So that's 6,500 multiplied by initial length. And then our initial length there. So our initial length there, we have for copper is 3 centimeters, so that's gonna be 3 times 10 to the minus 2, and then all over A, which is pi r squared, and then we said is 0.25 times 10 to the minus 2, and then all squared, because those were actually centimeters, and then multiply by Young's modulus of the copper, which is equal to 1.1 times 10 to the minus to the 11. So that's 1.1 multiplied by 10 raised to 11. So that's going to be 6,500 times 3 times 10 to the minus 2, and then divide by pi into 0.25 times 10 to the minus 2, and then squared multiplied by 1.1 times 10 raised to 11. So there I get change in length of 0.0009028 meters, which is equal to, if I multiply that by 1000, I get 0.09028 mm. So now the total change in length total will be equal to the change in length of the brass plus the change in length of copper. That's going to be, the brass was 0.1839, 0.1839 plus 0.09028, so that's gonna be 0.1839 plus 0.09028, then that's going to be 0.27418 meters, so that's millimeters. So that is the total change in length of those two. So now the next question now that we have this question. They are saying now a steel wire is strung between two supports attached to a ceiling. Initially there is no tension in the wire, it is horizontally. A 96 newtons picture is hung from the left of the wire as drawn in the illustration. So the ends of the wire make an angle of 26 degrees with respect to the horizontal, and they're saying what is the radius of the wire. So to find the radius of the wire, now assume that the wire is the same, it is uniform. That means now we're gonna have, now we have something like this there is inclined there. So let's say now is inclined in the wall, something like this. So initially it was horizontally like this, and then it has length initially. So now when okay, or let me represent it down here. So it was having a length initially, it was horizontally like this, attached there and then attached there. So now when we hang the weight of 96 newtons, now we can see that now it will deflect like this, and then now we have that weight of ours, and then that weight we are told that is what is 96 newton. So we'll assume that now it is exactly in the middle of the wire, such that the length this side is equal to the length that side. So when we hang this length, when we hang this, we notice that now the length will be larger than the initial length. So we will have a final length L there, of which we don't know how much is it, but we know that we have final length L. So that means now we're going to have this side 1 over 2L. We assume that now that is gonna be 1 over 2L also, and then this is our weight when we divide it in the middle, because it had an initial length L, and then now it was loaded and the length increased to L, and then we divide by 2, that's gonna be 1 over 2L and 1 over 2L on the other side. So now we know that the weight here is what is 96 newtons, and we know that we have theta here, we have theta there. So what do we do after that? So now we can actually, what we can do is actually that we can draw a free body diagram. So we have a weight here which is 96 newtons, and then we have that tension there, and then we have that tension there. So then let's say maybe this is T1 and then this is T2. So they are equal. This is T2. And then now taking the angles, you can see now that the angles are alternating, so that angle there will be the same as that angle there. So that means here you can have 26 degrees, and then this side 26 degrees, because those angles they will move from there and then from there to downwards there. So after doing that, we can actually draw a force diagram or a triangle for forces to complete the equilibrium forces. So that means now we can have this force directed downwards, and then that is 96 newtons, or let me say that is the weight of the picture, which is weight P. And then we have now that force directed that side, which is T2, and then we have that one directed that side, which is T1. So now we're gonna have here T2, and then we have here T1. And then obviously using these triangles we can find this angle to be 180 minus 2 times 26, and then that's gonna be 128 degrees, because that is a straight line. So now what we can do again is that now we can try to find the angles in this triangle of ours. So we know that the angle here, it was 26 degrees, and then we know that this total angle is 90. So if that is 90, we can say 90 minus 26, and then here we can have 64 degrees. And then if that is the case also here, we have the angle 26 alternate to that angle there on top, that's gonna be 26 degrees again, and with this one is inclined at an angle of 26, will be the same as that one. The inclination remain the same, that's gonna be 26 also. So if you say 26 plus 26, you get 52. So that means here we have an angle of 52 degrees. So you can also find that angle here, which is 180, sum of angles of a triangle, minus 64 minus 52, and then that's going to be 64 degrees. So what do we do after that? Now we can use sine rule to find one of the tension, and we said now we'll assume that the tension are the same. So because everything is symmetrical, so you can see now sine of 52 degrees divided by weight P. So is this angle opposite divided by the hypotenuse side. So that's going to be sine 52 divided by weight P, which we said is 96 newtons. And again, After that, we take any one there. We can say this 64 divided by the T1. So that's going to be sine of 64 degrees divided by T1, and then we can get our T1 there. So to get our T1, I'm going to say now sine of 52 divided by 96, and then I'm going to say now sine of 64 and then divided by the answer. I get that tension to be 109.496 newtons. So T1 is equal to T2 equal to 109.496 newtons. So it's reasonable to say they are equal because they are symmetrical both sides and the material is the same. The angles are also the same. So it's more reasonable to say now they are equal. So now we want the change in length. Now we know that the strain is equal to change in length over the initial length, and we know that strain is actually, according to this formula, is actually force multiplied by L initial over AE, and we know that strain also is equal to what? Stress over E, which is stress over Young's modulus. So now we know the force that is being applied. We might find the force that is being applied, which is the component there. So we know the force that is applied. That means in one of the springs here, we can say this one, for example, experiences a certain force here, and then that force we said we've calculated it. We said is 109.496. So that's 109.496 newtons. So we know the force that is being applied there on T1 on the first tension. So we do know it, and then what about the initial length? We do not know the initial length. That's what we don't know. So, but we know that strain, since we said that strain in the first equation is equal to change in length over the initial length, we know that is L minus, which is the final length, minus what? The initial length divided by the initial length. So if we can find the final length, or we can find the initial length, that will be better. So now we actually wanted the diameter. So let's go back to our drawing here. If we can divide this triangle of ours by 2, so let me redraw it. We said we have something like this. It was L initial and it extended to become this, and this was 1 over 2L final, and this was 1 over 2L final, and then we said at 26 degrees, we had 26 degrees, and then dividing by the 2, and we make that to be 90 degrees. So we can use that now to find L initial or L. So we can use adjacent. We can see that if that were the full distance here was L initial, that simply means that we have 1 over 2 L initial plus 1 over 2 L initial here. So that means now if we consider the triangle, one of the triangle here, or this triangle on the left, now we're going to say now adjacent divided by hypotenuse, which is cosine. Cosine of 26 degrees is equal to adjacent, which is 1 over 2L initial divided by hypotenuse, which is 1 over 2L. So now we can see that 1 over 2 will cancel 1 over 2, such that L initial will be L cosine of 26 degrees. So we're able to find the initial length in terms of the final length. So we can now say now strain is equal to length minus our initial length, which is length cosine of 26 degrees divided by initial length, which is L cosine of 26 degrees. So now I can say now strain is equal to, taking out L as a common factor, we're left with 1 minus cosine of 26 degrees, and then divide by L cosine of 26 degrees, and then that cancels that, and then E is equal to, we're left with 1 minus cosine of 26 degrees divided by cosine of 26 degrees. So that gives me 1 minus cosine of 26 divided by cosine of 26, and then that gives me 0.11 0.1126. So what do we do after getting that? We know now that the strain is equal to 0.1126, and then we said the strain is equal to force multiplied by length initially. We said is force multiplied by length initially over area multiplied by E. In fact, we can, to make things simple, we can use strain is equal to change in length over L initially, which is equal to, we said now is equal to the stress over E. If you remember this formula that I wrote first here, so that's gonna be stress over Young's modulus, and then we know that this one is 0.1126, which is equal to, obviously that's force over area. So if we change that one to be force over area, the stress we know is equal to what? Force divided by area. So that means now we can say, now in fact we can just say stress divided by Young's modulus. What we were given as Young's modulus, we're given 2 times 10 raised to 11. So that's going to be 2 times 10 raised to 11. So we can find stress. And then our stress will be 0.1126 multiplied by 2 multiplied by 10 raised to 11. And then that gives me 2.252 times 10 raised to 10. After that, we know that this is equal to force over area, and then this is equal to force over area. We know that is force, we have found it, and that's the one we say is 109.496. That's 109.496, and then divide by A. That means now we have 2.252 times 10 raised to 10 is equal to 109.496 over A, and then our area will be 109.496 over 2.52 2.252 times 10 raised to 10, and then that's going to be 109.496 divided by that, and then I get 4.862 times 10 to the minus 9, and then those are meters squared. And now, since we know now that if you have found area, we know area is equal to what? Area is equal to, what did they want? They wanted the radius. So what is the radius? They wanted the radius. You know that area is equal to pi r squared. That means from that area, which is 4.862 times 10 to the minus 9, we have pi multiplied by r squared. So our r will be now that divided by pi, and then we put the square root of that, and we get 0.0000393. So those are meters. So you can say R, if you multiply that by 1000, we're going to get 0.03934 or 393 millimeters. So that's how we can find that.